pleasure to introduce Pekka Parviainen from Aalto University in Finland. Pekka got his PhD from Helsinki University, and he is one of the top applicants for faculty position at the department. So on that occasion, he will give a lecture, learning Bayesian networks with bounded graph parameters. Sounds almost like it is related to the algorithms, people, right? But at least the last part of the title. We just talked about it before earlier today that machine learning in the view of Pekka has clearly links to algorithms. It has links to visualization, bioinformatics, and to security, right? So it seems like his interest touches upon almost all the groups we have here in the department. Without any more, please, the floor is yours.
Thank you, and good afternoon, everybody. So, like Petter said, this talk is about learning Bayesian networks with bounded graph parameters. I will start with a kind of introductory part where I will introduce what are Bayesian networks, and then also about learning Bayesian networks. And then I will move to my research and consider two kinds of Bayesian networks. Well, first, Bayesian network is bounded 3-bit, and then Bayesian networks is bounded vertex cover number. And I will then explain like why these particular classes are interesting. But let's start from the basics. So here the kind of background is that we have some variables or a set of variables, and we're interested in about their relations and the joint distributions. So I have an example here, a short example where we have 4 variables. It's whether a person is on time and then possible causes of being late. And in this kind of setup, a typical task that we have is that we observe one or more variables. For example, we can observe that person has forgotten to set his alarm on, and then we want to compute the probability of some other variable. For example, that what's the probability that the person is on time if he has forgotten to set his alarm. So this is kind of the setup. And to be able to do this latter task, then we need to have some kind of representation of the joint probability of all the variables. So if we have discrete variables, what we can do is that we can construct a joint probability table. So we have one row for each possible combination of the values of the variables. And here, for each row, we have a probability. So one parameter there. So here, the kind of problematic thing is that now already with 4 variables, we need 16 rows and 15 parameters to represent this distribution, and then the number of parameters grows exponentially with respect to the number of variables. So if we go to the distributions with dozens of variables, this kind of representation will not work. So we need to have some alternative way. Then luckily in real life applications, it's usually not that everything depends on everything. So there are independencies and conditional independencies between variables. So we say that two variables x and y are independent or marginally independent if knowing value of x does not help predict y or vice versa. So in our example, whether a person has an alarm on and whether a bus is late, they are independent of each other. So if we know that somebody forgot to put his alarm on, that does not help us to predict whether a bus is late or not. And then conditional independence, meaning that it means that if x and y are conditionally independent given z, this could be one variable or set of variables, then knowing such only z is is equally good than knowing both x and z when we try to predict y. So here we had this arm on and on time, so we can kind of clearly figure out that these are not independent. So if we know that you forgot to set your alarm, then it can raises the probability that you're late. However, if we know whether or not it overslept, then these are conditional independent given oversleeping. So if we knew that you wake up when you should not, when you plan to wake up, then it can, then knowing that your alarm was on or off, it doesn't matter when we predict whether you're on time. Then this independence is, we can think that it's a special case of conditional networks. So it has two parts. It has structure, which is a direct acyclic graph, or DAG for short, and then it has parameters. So the structure, we have one for each variable, and then we have these arcs between nodes. So this has clear semantics, kind of how do you read independence here. But for this talk, it's enough to know that if there is no arc between a pair of nodes, then those two variables are conditionally independent given some set. So we had that bus, late, and alarm on were independent, and alarm on and on time were independent given oversleeping. So we know that there are no edges here. So the independencies can be read from the structure. And then we have at each node we have this local conditional distribution for this variable given its parents in a graph. And then we get the joint distribution by just multiplying these local conditional distribution. So then why this kind of representation is nice? So one thing is that it's compact. So here the number of parameters that we need, it grows exponentially with respect to the maximum number of parents, but only linearly with respect to the nodes. So if each node has only few parents, then we can have significant savings in space. Then, although this is compact representation, it's flexible. So we still have the kind of the full joint distribution. So we can compute any conditional probability. So any probability of some set of variables given some other set of variables. This task is called inference. And then these are interpretable, so a human expert can just look the structure and then tell about properties and relations between variables, and then under some assumptions we can also draw some causal conclusions. So then when representation, then the question is that where do these networks come from? So one way would be that we have an expert who then constructs the network. But this requires domain knowledge, and also it really works if the network is small. So then the machine learners approaches then learn it from the data. So now we have samples from the joint distributions, and we want them to learn the network from that data. So we have now two parts. We have structure and parameters. Then the learning of the structure, it's hard problem, but then when we have the structure, then learning parameters is straightforward. So kind of that's why the research now concentrates on learning the structure. So there are two basic approaches for learning these networks. So constraint-based and score-based. So in constraint-based approach, we conduct some statistical tests to test conditional independencies between variables. And from those we get the kind of constraints, and then we try to construct a network that matches those conditional independencies. And the other approach is the score-based approach, where each network is assigned a score based on how well it fits to the data, and then we try to find a network that maximizes the score. And in this work, I will take this score-based approach. And typically, it happens so that the scores are decomposable, so that the score for the network is sum of local scores, and local scores are computed for node parent set pairs. So basically, the workflow is here that we have here data, then given some statistical principle, we compute local scores for this kind of node parent set pairs. And once we have scored, then we find the optimal networks. So basically, once we have these local scores, then this is a combinatorial problem, a discrete problem. So here is kind of the computational problem. So we have local scores, and then yes, so we want to find a directly acyclic graph that maximizes score. So we for each node we choose parent set with the kind of the constraint that the graph has to be acyclic. And here are several ways how to solve this. So one is using dynamic programming, which then it takes exponential time, and that does not scale until about 30 nodes. So in practice, we can use integer linear programming that can scale up in good cases to hundreds of variables. And these are now exact algorithms, so these are guaranteed to find optimum. Then of course we can use heuristics. And with integer linear programming, there is a nice thing that it's an anytime algorithm. So you can stop anytime, and then you can take the best feasible solution so far, and then you get an upper bound for the quality of the found network or the score. So this is now was kind of the introductory part. So now we will move to kind of my work. So bounding graph parameters. So here the only constraint was that the graph has to be acyclic, and now we will then have additional constraints. The next we will for example force it to have a small 3-bit. And I will shortly explain why this is interesting. And then let's start with 3-bit. So I'm not gonna formally define it here. So for those who don't know what 3-bit is, it's a property of undirected graph that intuitively tells how closely a graph resembles a tree. So here is 3-bit 1, 2, 3 example. And for those who know what 3-bit, then I might wonder that we had DAGs, so directed graphs. So when I say that DAG has bounded 3-bit or talk about DAGs 3-bit, so what I mean is that the 3-bit of the moralized graph of the DAG has bounded 3-bit. So so if we have a DAG like here, we construct a moralized graph that is an undirected graph as follows. We first take all arcs here and just drop the directions, and that is called a skeleton. And then we add, so for each pair of nodes that have a common child, so for example these two have a child, then we add an edge between them. And this is called moral graph. And we are now then working with this kind of. So then the question is that why on earth would one want to bound tree width of a Bayesian network? So this boils down to kind of what do you want to do after you have the network? And the common task is the inference, that we want to compute probability of some set of variables given some other set of variables. So doing this inference problem. Problem is that the inference is NP hard in general. However, it is fixed parameter tractable with respect to the tree width of the network. So if the network has low tree width, then we can do inference fast. However, there is no free lunches here. So here are some example networks learned from certain data sets. So here is network without any constraints. This is optimal network in general. This is optimal tree width 1, and this is optimal tree width 2 network. And what we observed that these low tree width networks are sparser. And from the beginning, we can recall that lack of edge means that the variables are conditionally independent. So when we force the learned network to have low tree width, we then force dependent variables to be independent. And that's why then this distribution is not as, or this representation is not as accurate as this. So there is a trade-off between inference speed and the fit of the model. But that's then for the modeler can control that. So here is now the problem statement that again we have an input, we have the local scores, and now we have in addition constant W, and we want to find a DAC whose moralized graph has tree width at most W and maximizes the score. So it is well known that if this W is 1, so we want to find an optimal tree. That can be done in polynomial time using the Chou algorithm. However, for any other bound, this problem is NP hard. So as people here know, kind of NP hardness should not prevent you from studying exact algorithms. So we have started here to develop algorithms for this problem. So first approach was to use dynamic programming. So we start with network for subsets of nodes and then grow and learn networks for larger combination. So this is actually, it's not for this case, this is how example about how this dynamic programming works for the Bayesian networks without this tree width constraint. With tree width constraint, this gets quite complicated, lots of nasty bookkeeping here, so we're not going through that algorithm in detail. And this is, of course, it has exponential running time, and it's really does not scale up in practice. So thus we had another approach for more practical learning. So this kind of the state of the art approach for learning Bayesian network is Indeterminate Programming, and we developed method for Indeterminate Programming for bounded tree width Bayesian networks, and this in most of cases scales up better than the dynamic programming. And I will come back to this kind of practical performance in a moment. But let's now move to the other type of graph parameters, so bounded vertex cover number Bayesian networks. So after we had studied the bounded tree width Bayesian network, and we had this territorial question that in that case we had tractable inference, but NP hard learning. So then the question is that are there any graph classes where we can have tractable inference, and then we can also learn an optimal network within that graph class in polynomial time. And it turns out that there is, so it bounded vertex cover number Bayesian networks are such. So vertex cover number upper bounds 3 of it, so we get tractable inference from there, and then we have a polynomial time algorithm for solving this. And this algorithm is rather simple, so we can go through it here. So we start by defining the vertex cover number. So vertex cover of a graph is a set of vertices such that at least one endpoint of each edge is in the vertex cover. So here the red nodes form a vertex cover. And then the vertex cover number is the size of the smallest vertex cover. So then again, the problem is that we have the local scores as input as well as a constant k, and then we want to find a DAG whose moral graph has vertex cover number equals k and then maximizes the score. So to do that, we have some observations. So first we observe that if we have in our DAG or in Bayesian network we have some node that is in the vertex cover, then it can have at most one parent outside of the vertex cover. Now this comes from the moralization. So if it has two or more parents outside vertex cover, then there would be the moralization edges that would not be covered. And then we also note that if the node is not in the vertex cover, then it cannot have parents outside vertex cover. Obviously that it would be uncovered too. So what we can now do, that we can partition nodes in two sets. We have a core, which consists of the vertex cover, and then parents of the nodes in the vertex cover. And because the size of the vertex cover is constant, and each of them can have at most one parent, this is of constant size. And then the rest of the nodes we call periphery. So if we know these sets, then kind of finding an optimal Bayesian network is easy. So these nodes in the periphery, they don't have any children, so they cannot be part of any cycle. So we can, for each of them, we can independently choose best parent set from the vertex cover. And here there are a constant number of possible parent sets, so it's for each of them it's constant time operation and in total linear time. And then we have this, which is our core. So here is the vertex cover and then the parents. And then so this can be done, for example, using the dynamic programming. And we have the constraints on the parent sets that we can have. And because this is constant size, then it's a constant time also. So then we just need to go through all possible choices of these core nodes. So vertex cover and parents of vertex cover. And because we have a vertex cover size k, so then we have here polynomial time requirement. Good. So this kind of looks a little nasty for practical purposes. So and here actually we have implemented and running. So here is the vertex cover number bound, and here is time on logarithm scale. So I ran this for 1 day, then stopped. So with 16 nodes, we can handle vertex cover number 4, and with 14, we can handle 5. And then we would want to, preferably we would want to go to hundreds of nodes and at least dozens. So this is not very good. So then the question is that can we here had this k here in the exponent, so could we get rid of that? So first thing is now that we have the local scores as an input, and so if we have vertex cover number k, each node can have at most k parents, because if it had more, then there would be a larger click in the moralized graph. So the input is already, or the k is in the exponent in the size of the input. So then we need to have some additional constraints. So consider a case that if we have at most 2 parents per variable. So could we have a fixed parameter tractable algorithm in that kind of case? However, the answer is probably not. So this problem is W1 hard. So we have a polynomial time algorithm that doesn't work in practice. So is all hope lost? Well, it's not. So this is what I learned from Fomin and Pratt's book when I read this line, that for every polynomial time algorithm that you have, there is an exponential time algorithm that I would rather run. So again, in this case, it's the integer linear programming that comes to our rescue. So it's kind of straightforward to go to this problem as an ILP and then solve it using solvers. So now we can kind of compare the bounded vertex cover Bayesian networks and bounded tree with Bayesian networks. So here we have one fixed data set. Red curve is bounded tree with network. Blue is bounded vertex cover. Here on x-axis we have now the bound. And in this upper plot we have score, and then here we have time. And we have 4-hour cutoff. So if we haven't solved we haven't found a provably optimal solution by then we take the best one and we also show the bound. So here is a small 9-node network. So both finish nicely. Of course, bounded vertex cover DAGs are more restricted class, so the scores are worse. So then when we go to larger networks, so then sometimes the bounded tree with case starts to struggle. So here we have the best bound solution, and then the top of the red curve tells the upper bound, so that we know that the best solution is some at most, score at most. So we also know that we usually run out of time. And this is even more pronounced here when we have 60 nodes. So sometimes we have very bad upper bound. So here for comparison, this is the score for the optimal DAG. However, what we note here is that the bounded vertex cover Bayesian networks are kind of, or the bounding vertex cover is very unflexible class. So we have here kind of huge differences in scores. So from practical purposes, in general, you should use the bounded tree with DAGs, because even the kind of suboptimal DAGs are way better than the bounded vertex cover DAGs. Good. So then, kind of to end this talk, I have some open questions in these topics that could be solved. So from theoretical perspective, one thing is that So one question to ask that are there any classes, graph classes, where we can find fixed parameter tractable, or algorithms that are fixed, problems that are fixed parameter tractable. So these are have hardly any practical significance, because already the on the vertex cover number DAX, it was kind of the class was not very powerful based on our results. Then there are also kind of questions overall kind of complexity landscape of these graph classes. One interesting class is this feedback vertex set, so which kind of lies between bounded vertex cover and bounded tree width. So and then because it's kind of that you have again a core that can be kind of dense, and then when you remove the rest of the graph is a tree, and we know that a tree can be learned in polynomial time. So it is plausible that we could find an algorithm or polynomial algorithm for this case. However, then because then we have a kind of a tree there, then there are lots of ways how we can induce cycles. So we don't have algorithm, and this might be an NP hard. So it's an open question. So then on a more practical side, so the setup here was that if we want to do fast inference, we kind of learn bounded tree Bayesian networks. So we learn a representation that is approximative in some sense, and then we do exact inference fast in that case. However, we could do things the other way around, that we learn network without any additional constraints and then do approximate inference. And then the question is that which one is better in which situation. And then another more practical thing is then kind of how to speed up this learning algorithm. So still kind of the interlinear programming, it's not very satisfiable with the results, so we want to go faster. Of course, when we have NP hard problems, there is probably comes to point when these exact algorithms don't scale up, so we need to resort to heuristics. But then kind of what interests me is that could we still keep some kind of quality guarantees and these heuristics. So that was all that I had, so thank you.
Thank you very much. Comments? Questions? Andy?
So if I understand you correctly, there's some hidden distribution from which you have drawn your observations,
yeah.
and then you're trying to construct a network in order to explain those observations, yeah. In some sense. So now when you say learning, it could be I misunderstood you, but when you say learning, you're saying that, okay, so these are the observations we have, now let's find the network whose sort of score with respect to this set of observations is the best possible.
Yes.
Yes. So there's also the different approach, like view of learning is that if you really think of your observations as being drawn from some distribution which is the ground truth, then with reasonable probability you shouldn't be too far away from the ground truth once you are done. So have you done any analysis of these kind of algorithms from that perspective?
No. So then of course it's, I mean, depends. So basically there is the scoring criterion. Mm-hmm. So many of them are what we call consistent scores. So then there is the asymptotic results that when the sample size goes to infinity, then the kind of with probability. So you find, or the highest scoring network is the ground root with probability 1, or it approaches there. So that kind of result. For some cases, people have this kind of back Bayesian things. We all have sample bounds, that how many samples you need to get under some error.
But do you know anything that if you are close to the highest scoring network, then you're also close to the ground? Like are there any? Because
so this is kind of depends on what you mean by close. So I mean, not necessarily close with respect to kind of the structure, because then you kind of have a different weights for the.
But statistical.
But yeah. So in sense that so typically kind of the scores is kind of some statistical thing. We have like Bayesian score. It's like marginal likelihood of the network. So we integrate over parameters and get it. So in statistical sense, yeah, you're close. And here we kind of bound tree with a vertex cover number. So we kind of force the network to be simpler than what the distribution is, and then kind of when we maximize score, it's kind of in some sense we kind of found the kind of the distribution that is closest to the ground truth within that class.
Yes.
So you chose these couple of restrictions to restrict your graph. So where does that intuition come from, or is it just intuition, or is it?
No. So this yes. So this is kind of well-known thing like from the long time that we have low tree width, then we have fast inference. And that was kind of our starting point. So if you want to be able to infer fast, then you want to have low tree width. So then there are theoretical results that say that if the exponential time hypothesis holds, then bounding any other graph parameter does not give you the tractable inference in all cases.
I guess my question was more, so you make this choice of sort of, this is the structure I'm going to be happy with. I mean, I could say I want a linear graph, like a chain, and that would not be a good model. So I would have, that would be a bad choice.
Yeah.
So I'm asking, like, so what's the intuition? Like, what makes you believe that restricting it in this way does not kind of distort the result from too far from what it actually is?
Yeah. So kind of course, here if you restrict it too much, then there's a trade-off between the fit. So this is basically the only time when you would want to use this is if you want to be able to do inference fast. So that's kind of the only motivation that I need to be able to do inference fast. So I'm willing to sacrifice some of the accuracy, and then you kind of need to somehow figure out what's the largest bound with which you can live. In that sense, that you somehow estimate how fast you need to infer, and then use the largest tree width bound that gives you that inference speed.
But you know how far off it's going to be from the
Well, I mean, so if you have time, you can of course compute score for like this network, and then you can kind of compare, for example, the score. And in theory, you could do like compute Kullback-Leibler distance between these, but it's in practice you cannot compute it because you need to sum over all possible values.
I mean, small cases you could get some.
Yeah. So in sense, but if you have small cases, then there's no point of using this because, like in examples here, so there's no point of bounding here because you can do this with brute force if you need.
So how large networks are typical today?
So, I mean, we would like to go to hundreds of graphs. So with the ILP, so without any tree-width or vertex cover bounds, they have solved several hundreds. Probably some networks with nearly 1,000 nodes to prove availability results.
Any other questions? Oh, many questions. Stefan.
Can you just say a few words about the the applications of these methods and how what you currently can do with the limitations in this challenging problem? Like, how close are you to addressing real world applications? Are there, like, orders of magnitude between what you can solve and what would be needed to address practical problems?
Yeah, so I'm working with mostly theory. So I'm working really with the application side. But I mean, they can do quite a lot thing in practice. So I mean, even for example, even though inference can be hard, kind of these modern solvers can solve quite large, or do inference with quite large network quite accurately. So I don't that kind of.
Because one obvious question is that, I mean, and I understand that that this is an interesting problem just from a theoretical point of view, but basically what you want to do is reconstruct the distribution, right? And now you're setting this up by saying, okay, basically this has a graph structure, this has a DAX structure. If and this is difficult to solve, but what if I can make another assumption that may be easier to solve, and that also allows me to reconstruct the distribution in the practical sense. So, what sort of is the main motivation for saying, okay, well, let's take this graph assumption more or less, despite it being difficult. Maybe, I mean, of course I understand. I mean, it's interesting to work on something difficult.
Yeah. So I'm not sure if there are kind of in that sense that there are probably not solution where you kind of could always do significantly better, because I mean, again, everything depends on everything. Yeah. So, but of course, this is not the only way. So for some distributions, we have, for example, Markov networks where we have undirected graphs, and then they are so they are kind of that. For some cases, this approach is better. For some cases, that is better. So it of course depends on the case.
You had another question, Alan?
So you had some data sets that you went into on your slides.
Yeah.
So what are these data sets from?
Yeah, so they are from a couple of competitors that so we are kind of, well, this is actually, I think this is housing data set from the, so there's the UCI, so University of California Irvine has this kind of machine learning data repository. This is from there, and I think most of those are originally, but so basically we took so data sets from a couple of papers and took union of those and run.
But do you know, so any of the ones that you showed on the picture, do they have any examples of what they're modeling? Is it like some diseases, or this looks like some tax?
So this is like housing prices in greater Boston area. So there's, yeah, so this is like crime and some texting and, yeah.
How it affects the price.
Yeah, yeah. So that is something ratio of something, yeah. And yeah, so that's how close the house is to Charles River. And
Yes.
Yeah, I'm not sure if I understand it correctly, but you said in order to increase inference speed, you need to put some or add more restrictions or more boundary conditions. Right?
Yes. So the smaller the tree width, the faster the inference.
But would that cause it can only be used to solve some specific problems?
No. So I mean, this is kind of a representation of the joint distribution. So you can then have any query you want for any set of variables given any other set of variables, and then all queries are guaranteed to be fast. But of course, then the problem is that this is now kind of the score kind of, we maximize the score of the whole network, but there can be like some parts of networks where we kind of get really bad fits. So for some specific queries, we can actually get kind of very bad results, and this approach does not give answer to that.
Okay.
So follow up on this one, how do you actually measure the network then? Is it with respect to predicting all the subset of variables? Or?
No. So here kind of the difficult thing is that, I mean, that's computationally heavy if you kind of go all queries.
Yeah. Well,
yeah. So usually we do just like we did here. So we have just the score, and that's kind of thing. And sometimes then you can do like you compute the marginal or some probabilities for marginals of two variables or something like that and compare to them. So that's kind of then the next step. But then the kind of more complex things you want to compute, then there's the computational time. So in sense that, I mean, that if we have this, so of course computing queries here is easy.
All right.
But then when you want to compare to them, so that's the hard thing.
So, talking about the data sets, did you run any kind of measurements against your competitors in other techniques, sort of practical learning?
Yeah. So we didn't, because we were the first. But then of course, yeah. So this is actually not the state of the art anymore. So there is another algorithm where they have a better implementation of integer programming that is somewhat better.
Right. Well, yes.
So better in the sense of running time, or better in the sense of the quality of?
Yeah, the kind of quality. So with fixed running time usually. So like here, the bound is here so much way off, so it would take ages that this to kind of convert. So basically, it's just that you stop at some point and then compare that.
Your talk certainly generated some interest and some questions. That's good. Pedro, any remarks, questions?
Did you think about approximation algorithms? Would it make any sense?
Yeah. So that's kind of on my list, to-do list. That because kind of these exact algorithms are kind of that there is probably a limit how far we can go. Is the kind of I think it kind of goes up here, that keeping some quality guarantees.
shall we thank Pekka again for this?